Welcome to G Fun Facts Online. Today we are stepping into the hushed, climate-controlled galleries of the world's great museums to witness a quiet revolution. This revolution is not being fought with brushstrokes, critical theory, or art historian debates, but with mass spectrometers and laser ablation systems. For centuries, the attribution of art, the act of determining who painted what and when, was the exclusive domain of the connoisseur. These were experts whose trained eyes could discern the hand of a master in the curve of a finger or the layering of a glaze. But we live in an age where forgers have become master technicians. They employ period-correct canvases and chemically synthesized pigments to fool the eye. Consequently, the eye is no longer enough. Enter the physicist and the geochemist. By analyzing the atomic soul of the materials themselves, specifically the isotopes that make up the lead in the paint, the carbon in the canvas, and the oxygen in the marble, science has unlocked a new level of truth. This is isotopic fingerprinting. It is a technique that reads the invisible diaries of atoms to reveal trade routes of the ancient world, expose multi-million-dollar fakes, and solve mysteries that have plagued art history for generations. In this episode, we will explore the science, the stories, and the seismic shifts this technology is causing in the $65 billion global art market. To understand how a machine can tell a Vermeer from a clever fake, we must first descend to the atomic level. At its core, every chemical element is defined by the number of protons in its nucleus. Carbon always has 6 protons. Lead always has 82. However, the number of neutrons in the nucleus can vary. These variants are called isotopes. Most carbon atoms in the universe are carbon-12, having 6 protons and 6 neutrons. But a tiny fraction is carbon-13, which has 7 neutrons, or the radioactive carbon-14, which has 8 neutrons. These isotopes are chemically identical. For example, a tree uses carbon-12 dioxide and carbon-13 dioxide almost interchangeably for photosynthesis. However, they have different masses. This brings us to the principle of fractionation. Because isotopes have slightly different masses, they behave slightly differently in physical and chemical processes. For instance, lighter isotopes like OXY-GeN16 evaporate from the ocean faster than heavier ones, like OXY-GeN18. In geology, when magma cools to form rock, certain isotopes lock into crystal structures at different rates depending on the temperature and pressure. In biology, plants actually prefer lighter carbon-12 over carbon-13 during photosynthesis. Over millions of years, these tiny preferences create unique signatures in the Earth's crust. Lead mined in Spain has a specific ratio of lead-206 to lead-207 that is distinct from lead mined in England or Italy. When a 17th century artist bought a tube of lead-white paint, he was unwittingly buying a material carrying the unique geologic signature of the mine from which it came. We categorize these into stable and radioactive isotopes. Stable isotopes like lead, strontium, oxygen, and sulfur do not decay. They remain fixed in a material forever and are used for provenance, which helps us determine where a material came from. Radioactive isotopes, like carbon-14, decay over time at a known rate. These are used for dating, helping us determine when an organism died, such as when the flax for a canvas was harvested. The transition from theory to art detective work requires sophisticated hardware. The days of needing a gram of material, which is a massive chunk in the context of a painting, are over. The workhorse of isotopic analysis is the mass spectrometer. It separates ions based on their mass-to-charge ratio. There is TIMS, or thermal ionization mass spectrometry, which is the gold standard for high precision, especially for lead isotopes. It requires dissolving the sample in acid, which is destructive but extremely accurate. Then there is MCICPMS, or multi-collector inductively coupled plasma mass spectrometry. This is a faster method that uses plasma to ionize the sample and is now the industry standard for provenance studies. Museum curators are understandably terrified of sampling. Destructive analysis is a dirty word in conservation. However, laser ablation has changed the game. Instead of cutting a sample with a scalpel, a laser beam is focused on the artwork, vaporizing a microscopic pit, often smaller than the width of a human hair and invisible to the naked eye. The vapor is sucked directly into the mass spectrometer. This quasi-non-destructive method allows scientists to analyze the lead-white pigment in a Rembrandt without leaving a visible mark. For carbon-14 dating, accelerator mass spectrometry, or AMS, is the breakthrough. Older beta-counting methods required burning large amounts of canvas. AMS counts the individual carbon-14 atoms, allowing dates to be obtained from a single thread or a speck of charcoal ink. Let us look at how this applies to pigments and provenance. The most prolific application of isotopic fingerprinting is tracing the origin of pigments. Lead white was the only high-quality white pigment available to European artists until the 19th century. It forms the base layer of nearly every Old Master painting and is mixed into almost every other color to add body. Lead ores, known as galena, vary significantly in their isotopic ratios based on the age of the rock formation. English lead has high ratios of lead 206 to lead 204, indicating a younger geological age. Alpine and German lead have lower ratios. Spanish lead has distinct signatures often found in Roman artifacts. A landmark study known as the Dutch Golden Age Project analyzed the lead white in 77 paintings by Dutch masters like Rembrandt, Vermeer, and Hals. The findings were fascinating. Before 1650, Dutch artists used lead from varied sources, likely mixed stocks. After the mid-17th century, there was a massive shift to a single, highly consistent source of lead. This was likely English lead, reflecting historical trade treaties and the impact of the English Civil War on mining. This science played a crucial role in the dispute over St. Praxedis, a painting attributed to Vermeer but contested. Lead isotope analysis showed the lead white matched the specific Dutch profile of Vermeer's other accepted works, distinct from Italian lead of the same period. This was a crucial piece of evidence in reattributing the work to the master. Moving further back in history, we encounter Egyptian blue, the world's first synthetic pigment. Its production requires copper. The mystery was whether Roman workshops imported the pigment from Egypt or made it themselves. By analyzing the lead isotopes often present as impurities in the copper ore, researchers found that Egyptian blue used in Roman frescoes often contained copper from local Italian sources or Iberian Spanish mines. This proved that the Romans had localized the high-tech production of this pigment rather than relying solely on imports from the Nile. Marble also presents a puzzle. White marble statues from Greece and Rome often look identical to the naked eye. Is it Parian marble, Pentelic, Carrara? Scientists use a combination of carbon-13 and oxygen-18 isotopes to tell them apart. Naxian marble has a distinct, heavy oxygen signature. Pentelic marble, used for the Parthenon, has a unique carbon-to-oxygen ratio overlap. This helps museums reassemble fragmented statues, perhaps matching a head in London to a torso in Rome, and detect forgeries. If a Greek kouros is carved from 19th century Carrara marble quarries that were not open in 500 BCE, it is instantly revealed as a fake. While stable isotopes tell us where, radioactive carbon-14 tells us when. Standard radiocarbon dating has an error margin of plus or minus 20 to 50 years. For art history, this is often too wide. Knowing a canvas is from 1600 to 1650 does not help distinguish a 1640 Rembrandt from a 1660 student copy. However, humanity unwittingly created the ultimate forensic tool in the mid-20th century. Between 1945 and 1963, prior to the Nuclear Test Ban Treaty, atmospheric nuclear weapons tests doubled the concentration of carbon-14 in the atmosphere. This is known as the bomb pulse effect. The implication is that any organic material, such as cotton canvas, flax, oil binder, or wood, grown after 1950, has a bomb peak signature, a massive spike in carbon-14. Because the carbon-14 levels rose and fell rapidly, scientists can date material from the late 20th century to within 1 or 2 years. A famous case study involves the Fernand Léger forgery. Peggy Guggenheim, the legendary collector, bought a painting titled Contraste de Forme, believing it to be a 1913 masterpiece by Fernand Léger. For decades, doubts swirled. In 2014, scientists at the INFN in Florence took a fiber of the canvas. The result showed the canvas contained the bomb pulse signature. The cotton was harvested no earlier than 1959. Since Léger died in 1955, the painting was indisputably a fake, painted on modern canvas. The bomb pulse provided a definitive terminus post quem, or earliest possible date. However, isotopes have limitations. Consider the case of the Gospel of Jesus' wife. In 2012, a papyrus fragment appeared in which Jesus seemingly refers to his wife. It caused a global theological firestorm. Carbon-14 dating of the papyrus returned a date of roughly 700 to 800 AD. This suggested the material was ancient. But there was a catch. Forgers often use ancient blank paper cut from the fly leaves of cheap ancient books to fool carbon-14 tests. While isotopes confirmed the papyrus was old, Raman spectroscopy of the ink showed it was simple carbon soot, and grammatical errors eventually exposed it as a modern forgery. This highlights a critical rule: isotopes date the material, not the artwork. Beyond paintings, isotopic analysis helps in ethics and archaeology. The illegal ivory trade decimates elephant populations. Isotopic analysis has become the primary forensic tool for law enforcement. Scientists have created isoscapes of Africa. By analyzing the carbon, nitrogen, and strontium in a seized tusk, they can pinpoint the specific national park or region where the elephant lived. Furthermore, bomb pulse carbon-14 can instantly tell if a piece of carved ivory is antique, meaning pre-1947 and legal to trade, or modern, meaning poached post-ban. This is the scientific backbone of modern wildlife crime prosecution. In the realm of ancient bronzes, the famous Riasi bronzes, discovered underwater in 1972, are masterpieces of Greek antiquity. Lead isotope analysis of the alloy traced the lead to specific mines, helping distinguish the original casting metal from the lead tenons used in later Roman repairs. This allowed historians to reconstruct the life history of the statues from their creation in Greece to their restoration in Rome before they were lost at sea. We must also discuss the high-profile detectives and the forgers they catch. Wolfgang Beltracchi is perhaps the most successful forger in history, earning millions by creating lost works of German expressionists. While Beltracchi was careful to buy old canvases to beat carbon-14 tests and mix his own paints, he was caught by a titanium mistake. X-ray fluorescence and microanalysis revealed traces of titanium in a painting attributed to Heinrich Campendonck, dated 1914. Titanium white was not commercially available as an artist's pigment until 1921. Beltracchi had used a tube of zinc white that was contaminated with titanium. While not strictly an isotopic case, it paved the way for the widespread adoption of rigorous scientific screening. Another famous case is the Vinland map, which purported to show a pre-Columbian Viking exploration of America. It is one of Yale University's most controversial possessions. Carbon-14 dating placed the parchment in the 1430s, consistent with authentic medieval material. However, recent analysis showed the ink contained anatase crystals with a specific morphology only created by 1920s industrial synthesis. A forger in the 20th century had bought a real 15th century book, tore out a blank page, and drew the map with modern ink. This case perfectly illustrates why isotopic dating of the support is never enough. The integration of isotopic analysis has shifted the legal and financial bedrock of the art world. Following scandals like the Noodler Gallery selling $60 million of fakes, many artist foundations dissolved their authentication boards to avoid lawsuits. This left a void in authentication. Scientific consultancies stepped in. Sotheby's acquired Orion Analytical in 2016, signaling that science is now part of the due diligence process for high-value lots. Courts are increasingly favoring empirical data over connoisseurship. In a lawsuit, an art historian's opinion that a painting feels wrong is subjective. An isotopic report stating that the lead isotope ratio corresponds to 19th century Australian ore, not 17th century Dutch ore, is empirical data. It is much harder to cross-examine a mass spectrometer. Of course, there are limitations. We can only match a sample to a source if we have data for that source. We need comprehensive isotopic maps of every historical mine in the world. Databases like the Oxford Archaeological Lead Isotope Database are a great start, but gaps remain. Sometimes, two different mines have surprisingly similar isotopic signatures. There is also the recycling problem. If an artist melted down old Roman lead pipes to make new paint, the isotopic date might be Roman while the painting is Renaissance. Looking to the future, machine learning algorithms are being trained to correlate isotopic data with chemical impurity profiles, creating super fingerprints. We are also moving toward portable devices that can perform initial screenings in the gallery, reducing the need to transport fragile masterpieces to a lab. Isotopic fingerprinting has fundamentally changed the narrative of art history. It has democratized truth, taking it out of the hands of a few elite experts and placing it into the peer-reviewed realm of physics and chemistry. For the art market, it offers security. For the historian, it offers a map of ancient trade and connection. And for the viewer, it offers a profound realization. A painting is not just an image, but a physical object, a collection of atoms harvested from the earth, carrying the memory of their creation across centuries to speak to us today. The silent witnesses have finally found their voice. Thank you for listening to Fun Facts Online.